Hello everyone. Welcome to this training presentation on StructureTool2D. This application is designed to support students taking a structural analysis course. It helps students connect theory with modeling, computation, plots, and reports. In this presentation, I will walk through the main features of the app and show the full workflow for analyzing beams, frames, and trusses. StructureTool2D is meant to support learning, not just produce answers. It helps students visualize structures, organize input data, run analysis, and interpret results. It is especially useful for checking hand calculations and understanding how loads, supports, and member properties affect structural behavior. It also helps students review internal force diagrams, deflected shapes, and reports in one environment. In this training session, we will follow a clear roadmap. We will begin with the main interface and overall workflow. Then we will move to Tab A, where the structure is created or loaded. After that, we will cover the Builder workflow and the Excel-based workflow. Next, we will study Tab BC, which includes stiffness analysis and the slope deflection method. Then we will move to Tab DE, which includes the unit load method and force method. Finally, we will look at examples and end with a workflow summary. This is the main interface of StructureTool2D. The application is organized into three main workflow tabs. These tabs guide the user from defining the structure, to running the analysis, to applying additional methods. The interface is designed so that the structure data prepared at the beginning can be used throughout the rest of the workflow. The first tab is A, Structure Data and Geometry. This is where the workflow begins. The second tab is BC, Stiffness and Slope Deflection. This tab is used for analysis, plotting, results, and reporting. The third tab is DE, Unit Load Method and Force Method. The structure defined in Tab A becomes the foundation for the methods used in the other tabs. Tab A is the starting point of the application. In this tab, the user either creates the structure visually using the builder or loads an existing Excel structure data file. This tab also provides support resources and a structure preview area. Before moving to analysis, the user should always confirm that the structure shown here is correct. There are two main ways to begin working in StructureTool2D. The first option is to open the builder and create the structure visually. The second option is to load an existing Excel structure data file. Both options lead to the same overall workflow. The choice depends on whether the user wants to build a new model or use prepared input data. Tab A also contains several support resources. The user can load a template, open the quick reference material, access the training content, or read the documentation. In addition, the structure preview area helps the user inspect the model visually. This is an important step because it gives an early opportunity to catch mistakes before analysis begins. The builder is the visual modeling environment in StructureTool2D. It allows the user to create and edit the structure directly on the screen. Nodes, members, supports, hinges, and loads can all be defined here. The builder is especially useful for teaching because it helps students see the structure as they create it. Before creating the structure, the user should first define the basic setup. This includes selecting the structure type, such as beam, frame, or truss, and choosing the units. The user can also set the canvas limits and the grid spacing. These settings help create a clear and organized model from the beginning. Next, the user defines the default member properties. These properties typically include material parameters and section properties such as modulus of elasticity, cross-sectional area, and moment of inertia. These values are important because they directly affect the structural response and the analysis results. Students should always check that these properties are entered correctly. The first geometric step in the builder is creating the nodes. Nodes represent the joints of the structure. To create them, the user selects the node tool and clicks on the canvas. The grid helps place the nodes accurately. The quality of the final model depends on the correct placement of these nodes. After defining the nodes, the next step is to create the members. Members connect the nodes and form the beam, frame, or truss. The user selects the member tool, clicks the start node, and then clicks the end node. This process is repeated until the full structural model is completed. Once the geometry is created, the supports must be assigned. Supports define how the structure is restrained. The user selects the support tool and places the required support type at the correct nodes. Common support types include pin, roller, and fixed supports. Since supports control the boundary conditions, they must be checked carefully. Some structures also require hinges at specific member ends. Hinges release moment transfer at the selected locations. The user applies them using the hinge tool. It is important to confirm that each hinge is applied at the correct end of the member because this can significantly change the structural response. After supports and hinges are defined, the loads are added. The builder supports both nodal loads and member loads. Nodal loads act directly at the joints, while member loads act along the structural members. These may include point loads or distributed loads. Students should pay close attention to the direction and sign of each load. The builder also includes dimensions and display controls. Dimensions help explain the geometry more clearly, especially in a teaching setting. Display controls allow the user to show or hide labels, nodes, axes, and the grid. These tools make the model easier to read and present. After the model has been created in the builder, the user saves and loads it into the main application workflow. This step transfers the structure into the standard StructureTool2D format so it can be used for analysis. At this point, the user should return to tab A and verify the structure preview once again. Instead of building the structure visually, the user can also load a prepared Excel structure data file. This file contains the geometry, connectivity, supports, properties, and load information. After the file is loaded, the application displays a preview of the structure. This preview should always be checked before analysis. Now let me explain the main categories of data the app reads when the structure Excel file is loaded instead of building the structure visually using the builder model. First, the structure type tells the app whether the model should be treated as a frame, a beam, or a truss. In this example, the structure type is a frame. Next, the counts for nodes, members, supports, and loads tell the app how many rows of each type of information it should read. These counts matter because the app uses them to interpret the rest of the file correctly. The node table defines the geometry. Each node has a node number, an x-coordinate, and a y-coordinate. This is how the app knows where each point is located in the structure. The member table defines connectivity and properties. Each member has a start node and an end node. The member table also provides the section and material properties used in the analysis. These include area, and moment of inertia. For beam and frame structures, the member table also includes hinge flags. That matters because hinge settings affect structural behavior, and they also influence which method sections are most suitable later in the app. The support table identifies the restrained nodes and the support type. This is how the app knows where the structure is fixed, pinned, or otherwise restrained. The load table records the external loading. Depending on the load type, the app reads whether the load acts at a node or on a member, together with the necessary magnitude and location information. For truss structures, the app still reads the same core categories of information. Nodes define geometry. Members define connectivity and properties. Supports define restraint. Loads define the applied actions which are limited to nodal loads. Tab BC is the next major stage of the workflow. This tab contains the stiffness analysis features and the slope deflection method. It allows the user to define analysis settings, generate plots, view results, and produce reports. For many students, this tab will be the main analysis area of the application. Before running the stiffness analysis, the required parameters must be set. These may include the number of elements per member, the deflected shape magnification factor, the scale factor for the internal force diagrams, and the structure type. These settings influence how the results and plots are generated, so they should be selected carefully. Before solving the structure, the user should first plot the structure geometry. This is one of the most important verification steps. It allows the user to inspect the undeformed model, including the geometry, supports, loads, and labels. If anything appears incorrect at this stage, the model should be corrected before analysis. Once the geometry has been checked, the user can run the stiffness analysis by selecting Analyze Structure. The application then processes the model and prepares the available outputs. These outputs depend on the type of structure being analyzed. This step is the main computational stage of the workflow. After the analysis is complete, the user can open the analysis results. These results typically include nodal displacements, support reactions, and member forces. The numerical output provides the exact values needed for interpretation and checking. Students should examine these values together with the corresponding plots. The deflected shape gives a visual representation of how the structure deforms under the applied loads. This view is especially useful for understanding the overall behavior of the structure. The shape is usually displayed with magnification, so it should be interpreted as a visual aid rather than the true scale of deformation. Internal force diagrams are essential in structural analysis. In this step, the application can generate bending moment, axial force, and shear force diagrams, depending on the structure type. For beams, the main focus is often moment and shear. For frames, moment, axial force, and shear are all important. For trusses, the focus is primarily on axial force. This plot combines the structure with the applied loads and the support reactions. It helps the user see how the structure balances the external loads. This view is useful for checking equilibrium and for interpreting the relationship between the loads and the resulting reactions. StructureTool2D also provides reporting tools. These reports help organize the analysis information and present it in a form that can be reviewed later. Reports are useful for both learning and documentation. They can also help students compare software output with manual solutions. One of the available reports is the Stiffness Solution Report. This report is especially useful in an educational setting because it presents the stiffness method solution in a more structured way. Students can use it to follow the analysis logic and compare it with classroom procedures or hand calculations. Another feature in Tab BC is the slope deflection method. This method is useful for suitable beam and frame problems. The application helps the student identify the unknowns and follow the slope deflection procedure in a structured way. This makes it a useful instructional feature for structural analysis courses. To use the slope deflection method, the user runs the method and then reviews the output. The application presents information such as the structure classification, unknown quantities, sideway condition, and solved values. This allows students to connect the method steps with the final solution. For the slope deflection method, the application can generate an analysis report and a summary report. The analysis report presents a broader view of the structural analysis, while the summary report provides a shorter overview of the key results. These reports help the user organize and communicate the outcome of the analysis. The final major tab is Tab DE. This tab contains the unit load method and the force method. These are additional analysis tools that help students study displacements and redundant reactions. The tab is divided into sections for trusses and for beam or frame problems. The unit load method is used to calculate displacement at a selected location and direction. The user selects the target node and the required direction, then runs the method. This feature is useful for students who are studying virtual work and displacement calculations in structural analysis. After running the unit load method, the application provides the method output. This output shows the selected node, the selected direction, and the computed displacement. Students should use this screen to connect the final displacement value with the method procedure, rather than reading the answer only as a number. The method output viewer gives a more detailed view of the unit load method calculation. This is useful when students want to review the intermediate values, the applied unit load case, and the calculation sequence. It helps students compare the software solution with the manual virtual work procedure. The analysis report is designed to follow the detailed steps of the hand calculation procedure. This makes it useful for students because they can compare the software-generated report with the method taught in class. Instead of only showing final results, the report helps students review the calculation flow and understand how the solution is developed. The summary report provides a shorter version of the key unit load method results, while the analysis report provides a more complete record of the calculation. Students should use these reports after checking the model, the selected node, and the selected direction. The force method is used to determine a redundant reaction for a suitable structure. The user selects the required node and direction, then runs the method. The output helps students understand compatibility, flexibility, and the role of redundance in indeterminate structures. Now we move to examples. This beam example highlights a simple but important case. It allows the student to study reactions, the deflected shape, the bending moment diagram, and the shear force diagram. This is often a good starting point for learning the workflow. This frame example demonstrates a more general structural case. Here the student can observe bending moment, axial force, and shear effects together. It is useful for understanding how vertical and horizontal members interact in a frame system. This truss example focuses on jointed structures that primarily carry axial force. It helps students observe how forces are distributed among the members and how the truss deforms under load. This is an important case in many introductory structural analysis courses. At this stage, it is useful to summarize the full workflow. Start in Tab A. Create the model in the builder or load the Excel structure file. Verify the preview and plot the geometry. Then move to Tab BC to run the stiffness analysis, inspect the results, and generate the required plots and reports. After that, use the slope deflection method, unit load method, or force method as needed. Throughout the process, always verify the model before relying on the results. This completes the training presentation on StructureTool2D. The application is a useful educational tool for students studying beams, frames, and trusses. It supports modeling, analysis, interpretation of results, and comparison with hand calculations. Thank you for watching, and I hope this presentation helps you use StructureTool2D effectively in your structural analysis course.